Understanding time complexity in sorting algorithms.
Time complexity measures how an algorithm's running time increases as the input size grows. For sorting algorithms, analyzing time complexity helps us choose the best method for different situations. We'll break down popular algorithms and learn simple techniques to calculate their time complexity, making it easy to compare how fast each one works as data size increases.
Analyzing bubble sort's time complexity.
Bubble sort repeatedly steps through the list, compares adjacent elements, and swaps them if needed. In the worst case, every element must be compared with every other, leading to O of n squared, or O of n squared, time complexity. This means if you double your input size, the sort could take roughly 4 times as long. Bubble sort is simple, but inefficient for large lists.
Understanding merge sort efficiency.
Merge sort divides the list into halves until each part is just one item, then merges them back together in order. At each step, the list is split, creating levels equal to the logarithm of the input size, and at each level, all items are processed. This results in O n log n, time complexity, making merge sort much faster than bubble sort for large datasets.
Quicksort and its time complexity.
Quicksort picks a pivot item, partitions the list into smaller and larger elements, and recursively sorts the sublists. On average, it takes O of n log n time, similar to merge sort. However, in the worst case, where the pivot choices are poor, quicksort degrades to O of n squared. Good pivot strategies can keep quicksort running efficiently in practice.
Comparing and calculating time complexities.
To analyze time complexity, count key operations such as comparisons and swaps. Use big O notation to describe how the number of steps grows with input size. Bubble sort is O n squared. Merge sort is O n log n. And quicksort is O n log n on average. Choosing the right algorithm depends on data size, order, and performance needs.